Remember, we've talked previously about unit vectors, and that's terminology that if you haven't heard it before, it takes a while to get used to, but we will get used to it. A unit vector is nothing more than a vector that has a magnitude of 1. It's just a 1 unit long vector. Okay, 1 unit long. Now, that doesn't mean that our horizontal displacement's 1 and our vertical displacement's 1. That vector would actually have a magnitude of the square root of 2. Now, we're talking about something that's only 1 unit long. And if it goes at a slant, then that 1 unit doesn't mean we're moving horizontally or vertically 1 unit. Oh, okay. Anyway, so this discussion is about creating a unit vector from a given vector. And the way it's stated, as you can see, is finding a unit vector in the direction of some given vector v. So v is a given vector. And from that given vector, we want to create a vector u that's 1 unit long, a unit vector, but it's exactly the same direction as v. It's parallel to v. Okay, not only parallel, but it's in the same direction. And so this is the process that we use. U is what we're trying to create, a unit vector. What we're given is v. And so it's simply this idea that, remember, okay, let's suppose vector v is currently 2 units long. Well, if we wanted to scale that so that it's 1 unit long, we'd multiply it by 1/2. See, if it was 2 units long, we'd multiply it by 1/2, or we would divide it by 2. If it was 3 units long and we wanted it to be 1 unit long, then we would divide it by 3. We'd scale it back. So instead of being 3 units long, we want it to be 1, we'd divide by 3, or we'd multiply by 1/3. And that's really what this is telling us to do. What we do, see, remember, this represents the magnitude of v currently, okay, the magnitude of v. And so if we want v to be just 1 unit long, then we're going to multiply it by the reciprocal of its magnitude. If it's 2 units long, we'd multiply it by 1/2. And that 2 and the 1/2 is the magnitude of v. So in a nutshell, this is the way it's defined. If we want a unit vector u that's in the same direction of a vector v, we take the vector v and we divide it by its magnitude, which is equivalent to multiplying the vector v by 1 over the magnitude of v. And this multiplication is scalar multiplication. It's easy to do. Our job is to, our job is to remember this formula. And when we get to where we have lots of formulas to remember, until we get used to them, they all seem foreign. Now notice here I'm just making a note that the magnitude of this vector u is a 1, and that's what it means to be, of course, a unit vector. And that's what we're trying to create. So we might have a problem like this. So we're supposed to find a unit vector. Find a unit vector that's in the same direction of the vector v, which is given by these components, and then verify that the result has a magnitude of 1, in fact. Okay. So let's remember from above, we're creating a unit vector u. How do we do it? We take the given vector v and we divide by its magnitude. Or take the given vector v and multiply, scalar multiply, with the reciprocal of its magnitude. And so the first job we have to accomplish is figuring out what the magnitude of v is. And so remember how we find the magnitude of v. It would be the square root of the first component squared plus the second component squared, which I've shown here. When we square -2, we get 4, of course. When we square 5, we get 25. So we have the square root of 29. So that's the magnitude of v. Okay, well, now we're ready to create u. So u is 1 over the magnitude of v. There's the magnitude of v. Dot product with, not dot product, pardon me, scalar product. Have I been saying dot product? Scalar multiplication, scalar product with the vector v. Here it is. And so we multiply each of these components by 1 over the magnitude, which is the equivalent of saying take each component and divide by the magnitude. Those are equivalent. So here we have this vector, as ugly as it is, as ugly as these components are, this vector is a unit vector. It's 1 unit long, and it is going in exactly the same direction as our original vector. Remember, multiplying by a scalar that's positive doesn't change the direction. It only changes the magnitude. Well, the next part of the problem was to actually show that the vector u that we've created actually is a unit vector. We already know that it's in the same direction of v because we just multiplied v by a positive scalar. But is it really 1 unit long, as I promised? Well, how would we calculate the magnitude? Well, it's the square root of the sum of the squares of the components. So we'd have to square this first component, and I've shown that here, plus square this second component, which I've shown here. Of course, when we square a negative, we get positive. When we square a fraction, we square the numerator, which here we get 4, and square the denominator. Well, when we square square root of 29, we get 29. And likewise, when we square this fraction, we would get a 25 in the numerator and a 29 in the denominator. Now, under that square root, we have these two fractions with a common denominator. We add them together by adding their numerators. And so we have 29 over 29, which of course is 1. So we have the square root of 1, which is 1. And that's the verification then that the magnitude of u, which we were told we expected to be 1 because it's supposed to be a unit vector. Once again, what we have done is taken a given vector, okay, and create a unit vector that is in the same direction of the given vector, a vector of magnitude 1. Well, there are two, these are called by different names, but there's two special unit vectors. And here in our book, I think they call them the standard unit vectors. Some places they're called the basis unit vectors. But there's two special vectors, unit vectors, and one is perfectly horizontal that we call I, and the other one is perfectly vertical that we call J. So the unit vector I is horizontal, so it has a horizontal displacement of 1, but if it's horizontal, the vertical displacement is 0. So the vector I has that special name, has a first component of 1 and a second component of 0. And when we graph that, we can clearly see that it's 1 unit long. Now the vector j, and it goes by that name, the vector j only goes vertically. So it has a 0 horizontal displacement and a vertical displacement of 1. Horizontal displacement 0, vertical displacement 1. When we draw that vector, we can see that it's 1 unit long. So it's clear that those are unit vectors. And we could go further and we could prove that the magnitude is 1, but I don't think that we need to go to that trouble. Now, these two vectors are used, and you may have already run across this, these two vectors are used to write any vector as what we call a linear combination of those two. Remember, we can add vectors together. Well, any vector that we're given can be written as some scalar times I plus some scalar times j. Okay, any vector that we're given. So the way we would do that, so we've got this vector that has first component v sub 1, second component v sub 2. Well, the vector v, then, we could think of taking the number v sub 1 and multiplying it times I, which is this vector, 1, 0. Okay, and just thinking backwards, what would that give us? See, that would be a v sub 1 in this position and a 0 in this position. And if we wrote v sub 2 times the vector 0, 1, v sub 2 times 0 is still 0, v sub 2 times 1 is v sub 2. So we would be adding a v sub 1 to a 0, that would give v sub 1, and we'd be adding a 0 to a v sub 2, that gives us v sub 2. And of course, these two vectors are just I and j. So, in a nutshell, it boils down to this vector v, we can change the component form into a linear combination of I and j. That is, this component times I plus this component times j. Now, quite frankly, I prefer the component form. This form, there's nothing wrong with it, and our book uses it quite frequently, and maybe even more than it uses the component form. But there's a lot of extra busyness here. I prefer the form here, and either is okay to use. Now, the V sub 1 and V sub 2, again, are called the horizontal and vertical components of V, as we've already talked about. And as I already mentioned, any vector can be expressed as a linear combination of the standard unit vectors I and j. And I already said that above. So practice on the next page. We're going to write a vector as a combination of the standard unit vectors. And this has got a little twist in it. By the way, here, U just represents a vector, not particularly a unit vector, okay? We're going to use I and j, the particular standard unit vector. So U is just a vector, and it's a vector that has an initial point of 2, -5, and a terminal point of -1, 3. So we're asked to write U as a linear combination of the standard unit vectors I and j. Well, the first obstacle is that we need to first we need to write U in component form. We need to find the horizontal and vertical components of U based on our initial point and our terminal point of the vector. And so that's where we start, as we begin by writing the component form of the vector V. Remember how we do that is we want to know the horizontal displacement, so we take the ending x value, if you will, and subtract the beginning x value. Ending subtract beginning, -1 subtract 2. Okay? And we take the ending y value, terminal point, ending y value, and subtract the beginning y value, which would be 3 subtract -5, if I've written that here. So 1 subtract -2 is -3, and 3 subtract -5 is 8. And so the component form of this vector U is -3, 8. And once we know that component form, then we use this horizontal component as a scalar multiplier times I, and this vertical component of the vector as a scalar multiplier times j. And of course, we add those two vectors together. Remember, this together is a vector, and this is together a vector, and we're adding them, and it gives that result. What else are we supposed to do here? I don't recall. So let's see. Oh, well, while we're here, you know, this just asks us to write these as a linear combination, and that's what we've done of I and j. But just so that we know how these operations, addition and subtraction and so on, look when we're dealing with the component form. So see, the linear combination form in terms of i's and j's. So we've already got U in terms of I and j, and let's assume we've got some other vector V that can be written in terms of I and j, and it's 2i minus j. In component form, this would be 2, -1. 2, the coefficient, if you will, of the j vector. So we're supposed to find 2u minus 3v. Well, here's how we would do it. We would take u, which has these components, and we would multiply it by 2, and that's just like distributing. We'd multiply, here's u, we would distribute the 2. Minus 3 times v. Well, here's our minus 3, and here's our v, and so we would distribute that 3 as well. Okay, so here's the way I would actually distribute that -3. So 2 times -3i is -6i, 2 times plus 8j is 16j, -3 times 2i is -6i, -3 times -j is positive 3j. And then we would add the I pieces together. -6i plus -6i is -12i. 16j plus 3j is 19j. And so that's the result of of calculating 2u minus 3v. So again, that's even a little more algebraic than what we were used to before, isn't it? And we could subtract in a similar way, okay? And if we're finding magnitude, we would just, if we wanted to find the magnitude of u, it would be the square root of this negative 3 squared plus this 8 squared. Well, after this, there's one more video dealing with vectors and this introduction to vectors and algebraic operations on vectors. And it has to do with what are called direction angles, defining the direction. You know, here we have this algebraic way of writing vectors component-wise or in terms of I and j. And of course, when we graph them, we can see the direction, but there's a way to talk about an angle that defines the direction, and that's what is done in the last of this introduction to vectors. So please take a look at that.